For 60 years, the advancement of computing followed a predictable trajectory, shrinking the silicon transistor to pack more performance into a smaller space. But at the 7-nanometer threshold, that geometric march hit an invisible physical wall. At this scale, the insulating barriers inside logic gates thinned to the width of just a few atoms. Here, the laws of classical physics do not simply fade, they actively revolt, giving way to chaotic quantum mechanics. This physical boundary threatens to halt the continuous expansion of enterprise cloud networks and neural networks that sustain modern economic growth. To understand the finality of this wall, we have to look back to the planar field effect transistor, the foundational structure of the digital age. This architecture works as a simple binary valve. A source electrode injects electrons into a channel, a drain collects them, and a gate sitting flat on top applies a voltage to either permit or block the flow. But as the gate length shrinks below 20 nanometers, the physical distance becomes so minuscule that the gate loses its electrostatic control. Even when the transistor is ostensibly turned off, electrons leak continuously underneath the gate. At this scale, electrons stop behaving like predictable spheres flowing through a pipe. Driven by the Heisenberg uncertainty principle, they start to behave as wave functions, spontaneously teleporting directly through the solid material of the closed gate. This uncontrollable leakage causes processors to draw fatal amounts of power, melting their own microscopic circuits and corrupting the logic of 0 and 1. Engineers realized that to maintain control, they had to stop treating electrons as point masses and radically alter the geometric boundaries of the transistor itself. By analyzing the Schrödinger equation, physicists realized they could maximize electrostatic control by completely encapsulating the conductive channel within the gate. The evolutionary step was the 3D FinFET, lifting the silicon channel into a vertical fin wrapped by the gate on 3 sides. This evolved into Gate-All-Around nanosheets, slicing the fin into isolated layers, with the gate wrapping entirely around every single channel. This 3-dimensional topology compresses the depletion region, driving the probability of quantum tunneling back towards 0. But translating this mathematical model into physical reality triggered a series of catastrophic structural failures on the factory floor. Growing alternating atomic-scale layers of silicon and silicon germanium created severe mechanical strain within the crystal lattice, causing early prototypes to disintegrate. When the germanium was etched away to leave the pure silicon nanosheets suspended in midair, the structures were as fragile as microscopic bridges. Entire arrays snapped under invisible capillary forces. If chemical etchants deviated by a fraction of a percent, the suspended nanosheets would violently collapse. These fractional deviations reduced millions of dollars in experimental wafers to shattered silicon dust, halting the multi-billion-dollar manufacturing lines. Scaling these laboratory fixes required constructing the EUV cleanroom, a manufacturing environment requiring billions in capital investment to print sub-nanometer geometries. Inside these facilities, monolithic multi-axis robotic corridors operate under ultra-high vacuum conditions to build 3-dimensional atomic structures across 12-inch wafers. Engineers deploy atomic layer etching, a self-limiting chemical process that removes precisely 1 atomic layer of material per cycle, preventing the structural collapse of the nanosheets. This meticulous process allows workers to monitor the assembly of billions of transistors per chip with near-atomic accuracy. The core of the facility is the ASML lithography machine. It blasts molten tin droplets with high-power lasers to create a plasma that emits light at a wavelength of 13.5 nanometers. Advanced machine learning algorithms adjust plasma fields and chemical gas flows in real time to print these complex GAA nanosheet topologies with sub-nanometer overlay accuracy. This self-correcting cybernetic organism successfully transforms a volatile quantum anomaly into a mass-produced commodity. Mastering the 3rd dimension merely bought time before humanity hit the next inevitable physical wall. Nanosheets are now being pushed to their thermodynamic limits. We are reaching the scale of the silicon atom itself, which measures approximately 0.2 nanometers in diameter. At these dimensions, the atomic scale roughness of the material interfaces creates severe electron scattering. This scattering causes electrical resistance to spike exponentially, destroying the efficiency gained by moving to 3-dimensional structures. The industry is now pushing the element of silicon to its absolute physical and thermodynamic limits. Beyond the scale of the atom lies the final thermodynamic boundary of classical computation, the Landauer limit. This equation defines the theoretical minimum energy required to erase a single bit of information. As switching energies approach this floor, the thermal noise of the universe itself begins to flip bits at random, introducing unshieldable chaos into classical logic. To find a way around this energy floor, researchers are racing towards two-dimensional transition metal dichalcogenides and the potential of topological quantum computing. The quantum anomalies that first appeared at the 7-nanometer mark have not been conquered, they have only been contained, and they are waiting at the next atomic boundary for logic to break once again.